Okay, welcome back. It's loud. Yeah, welcome back. So according to the schedule, today we're supposed to do something called the quotient topology. Apologies, we will not do that. I decided to modify the schedule because some of you asked some questions last time, and I think it's a good moment to just go into there. We can switch with no problem. So lecture 10, it's going to be about sequences. And well, when do they converge? So this is based on section 17 or chapter 17 from anchors. So the idea here should be something that we kind of know. So for us, the topology that we know is that the standard topology on the reals. And then also maybe if you know some multivariable calculus, then the say standard topology on Rn, which we now know come either from a product topology or from a Euclidean metric topology. And in those situations, we have these notions of when you have a sequence, when does a sequence converges to something? And this is kind of what we want to discuss today. So definition one, let's take topological space. We defined this notion of neighborhood of a point, and we defined the notion of basis for a topology. Now what we want is somehow the intersection of these two notions. So let's take a point in X, A. Then what we're going to define is a neighborhood basis of A is going to be a collection of neighborhoods. That's not new. Let's call this B sub A of A. So that's to be expected. We like a collection of neighborhoods, but we wanted to have some property, and the property is the following, such that kind of the local description of a topology coming from a basis. So, but very local to A. For every neighborhood, let me just abbreviate neighborhood U of A, there exists some basic neighbor B in what we're calling BA, such that B is inside of U. So I could draw a picture, but it will be kind of nonsense. You have a collection of neighborhoods. Here's your A. And then what you want is for any neighborhood, suppose I'm using blue to denote an arbitrary neighborhood U, I want to have one of these distinguished neighborhoods B. Maybe I will use squares here, contained in U. And I know both will contain A, if both are neighborhoods of A. So it's very similar to the local description of what we call T of B, the topology coming from a basis, but it's extremely local because it's neighborhoods and neighborhoods of a given point. Are we okay with this definition? So of course, examples. So by the way, this is something you can introduce before even describing what a basis is. Yeah. So assume example one. Assume X is discrete. So we have a discrete space. That means a set with a discrete topology. Bases of neighborhoods will not be unique by any means. Same way bases are not unique. If X is discrete and you take some point A in X, then what are neighborhoods of X? Of A, sorry. What are neighborhoods of A? Well, opens here are just any subset. So neighborhood of A will be a set containing A. Any subset containing A is a neighborhood of A. So if we want to find a basic family, namely something contained in any open containing A, we can just take A to be the collection with just one neighborhood. So it's a collection of neighborhoods. Then this is a neighborhood basis of A. And in general, this will work in any space where you have a point which is open as a set. So if your singleton is open, then this will always be a neighborhood basis for that point. Yeah.
Because in the definition we say a neighborhood basis. Oh, sorry, that's the definition of neighborhood basis. That's what the definition one is. You're defining what a neighborhood basis is, right? Yes. So a neighborhood basis is where you have some basis such that every A has a neighborhood, or every U, right? There's a neighborhood around every point in B, right? For every A and B, there's a neighborhood around that point, right? That's the definition of neighborhood basis. Oh, wait. So for every B, because essentially that's your defined neighborhood basis there, and then here the example is you have a set, and then you define a neighborhood basis as the set of that the set of that element A, right?
Yeah, maybe let me give some more examples. I don't sure if I understand the question. So
example one.
yeah, absolutely.
If we throw also into that collection
Any other
a
thing.
set of A and B, that would also be a neighborhood.
You can expand it. Absolutely, yeah. Probably you're never going to use that one.
Yeah.
But you can. You can even like put the entire X if you want.
Because X is discrete, every A in X will be open, right?
Right, that's the fundamental point here. And this is true for any space where you have a point that's open as a singleton. So assume now X instead of discrete is what we call trivial. So kind of the other extreme point here is equipped with a trivial topology. And we take, so we take a point. So neighborhoods of A is just the entire space. So in this case, this guy, the entire space, collection of neighborhoods is just the neighborhood given by the entire space is a basis, is a neighborhood basis of A. Right? Because you take any neighborhood of A, then it needs to be X. Yep.
The neighborhood basis is not a basis for topology.
No, it's very local. But if you have a neighborhood basis for each point and consider the union of all of them, they should give you a basis. Yeah. Okay, so part 3. Metric spaces. If we take a metric space. So when I say this, I take a metric space. What I mean is I have a metric space, and then I consider the metric topology. And we take a point. Let's A in X. Now, please give me a basis for neighborhoods of A. Please give me a basis here. Balls, which sort of balls? Centered A. Radius, arbitrary radius. Is a neighborhood basis of A. Maybe should be called neighborhood basis at A, but yep.
Because that, if XD, is that capital X or lowercase?
Capital. Oops. Capital X.
In the definition, like they said, there exists a B in BA.
Mhm.
Does that B have to be open or is it just random?
No, remember neighborhoods don't need to be open, but they need to contain an open containing A.
Oh, so the B here is just still a neighborhood of A.
Right, just a neighborhood, not necessarily open. Now, probably most of the time you will be interested in open neighborhoods of A. Those are just open sets containing A. So yeah, what you mean is maybe you can say maybe the closure of the ball, namely the distance at most epsilon, including epsilon, then that also will work. But yeah, most of the times when we're cooking up bases, we want open sets, not part of the definition. Okay, so those are some examples. Maybe I should say that this needs to be, maybe we need a proof for this, but the proof will be not even a homework assignment. Proof is just an exercise for you to go through the definition, but shouldn't come as a surprise. Okay, so that's for bases. And now I promised you we're going to consider sequences. So definition 2. Well, maybe just to be sure we're all on the same page here, let me fix the notation that I will use for sequences. So notation. So this is kind of a definition, but not really. So a sequence on a set X. So you don't need a topology on set to have a sequence. Well, it's just a function. It's a function from the positive integers into X. Right? Usually denoted as a function. Instead of X of n, we do X sub n. And to be honest, I will not use this notation. The notation I would use is, so it's kind of, I'm considering the image here, but I'm doing parentheses because I want to emphasize there is an order here. And that's the standard notation for a sequence, to denote a sequence. So yeah, that's what a sequence is. Sometimes you don't use this, just say parenthesis xn, and you know what we mean. So definition 2, yeah, maybe this should have its own black. Definition 2. So I will start with the topological space now. So let X be a topological space. Let's take a point. So I will use small x here. Sorry if it's confusing. X should be what's called A before. Now I will take a sequence. So we say that a sequence, I will use xn in X, converges to X, the point that we have. So this is what I'm defining. So let me give you the definition, and then we'll see why this makes sense. If for every open set, let's call it U, containing X, so this U is just an open neighborhood of X, could be switched for any neighborhood. So if for every open containing X, there exists some positive integer, capital N, because we want to think it's big, such that if you take an index that's bigger than or equal to your given capital N, then your sequence lives in the given neighborhood U. So what we're saying is something like, here's your X. You take an arbitrary open neighborhood of X, arbitrary U. You have your sequence, X1, X2, X3, X4. We don't know really what the sequence is doing, but we need to be sure at some point for that U, there will be some N such that the sequence starts to live inside of U. And the idea here is, since we're doing this for any U, maybe you can like take U here, like V. Of course, this is nonsense, but you can like somehow make it smaller. And the sequence also needs to live there at some point. So also needs to get here, let's say, xm, xm plus 1, and so on. So that's what we're measuring. Yep. Yeah, to what?
Oh.
Yeah. Mm-hmm. Mm-hmm. Yeah, we'll get there. That's the point for today. Yeah.
We talk about the sequence is lowercase n, but in the variant you say then xn is in U, that's capital X.
No, x sub n is always small. The only capital X is this one. Oh, and this one also. Okay. Sorry?
Dressing up the X's, there's one more application.
Xn in N.
Oh, thank you. Here you go. Make sense? Yep.
So I think what we're doing is we're just redefining all of these real analysis terms using sets. So like previously when we think about this on the number line where for a sufficiently large n, your numbers get in some interval, right? X
Yeah.
X minus seven, X not, or X not X, seven minus A, whatever.
But now we're talking about it in terms of sets, where the points get in.
Well, the thing is not really sets. The important thing is that you have a topology. So everything here depends on a topology. It's not just set theory. Yeah. So when I say something like for every open set, that's really saying something about the topology instead of just X. Okay, so kind of to get our hands dirty with this concept, let's do a lemma. Maybe I should say, let's continue here. So in this case, so definition 2 continued. I just want to introduce more terminology. So in this case, we say that the point X is a limit of Xn of the sequence. And I'm saying the limit. And just write Xn goes to X. Okay, so now let's start with a sequence. Let's take a sequence in a topological space, capital X. And let's take a point. That should be a limit for the sequence. Then the lemma is saying that the following are equivalent. The first one is, well, Xn converges to X. So the sequence converges to the point X. The second one is, I want to use that terminology. Assume we have a Bx, B sub X is a neighborhood basis. Of point X. Then for every element in this basis of neighborhoods, there exists some capital N such that, so instead of writing this, if then, because what I'm trying to do here is like the usual analysis, X minus A smaller than delta implies Fx minus Fa smaller than epsilon. I would just say such that Xn lives in B for any n bigger than or equal to n. Absolute same thing. And the third one is, assume we have a subbasis now. So notice we didn't define what's a subbasis of neighborhoods or a neighborhood subbasis, and that's because that's mostly nonsense, but not really. So assume S is the subbasis of the topological space X. Then the same thing. Then for every set in the subbasis, but now I need to be sure it contains the point. Then same thing. There exists some capital N such that Xn lives in that subbasic set when you let your index be bigger than or equal to the given n. So this should come as a consequence of the definitions mostly, because the definitions, both definitions say something about every open set or every neighbor. So it shouldn't be, should be probably just a formal argument. let's do 1 implies 2. So we assume xn converges to x, and we assume Vx is a neighborhood basis. So we assume these two things. Assume xn converges to x, and Vx, and maybe let's say, and let Vx be a neighborhood basis of x. By the way, there's always a neighborhood basis. You can just take all open sets containing x. Okay. We want to prove that for every element in the neighborhood basis, then something. So take some arbitrary b in this Vx. And now I want to use this. That's the only thing I know. This B set might not be open, but it's a neighborhood of x. So it contains an open containing x. And then we're done. So since each B here, since every here, oh, there you go. Where's my definition? There you go. Since each B is a neighborhood, since B is a neighborhood of x, of point x, there exists some open set U with x in U inside of B. And now for that U, we know the sequence will eventually land in U. That's what this means. Eventually, the sequence will land in U. For that U, there exists some n such that xn lives in U whenever your index is bigger than or equal to your capital N. And now we're done, just because U is a subset of B. So since U is a subset of B, we also have what we want. So xn lives in B whenever your index is greater than or equal to the capital N. So very formal. Just using that a neighborhood might not be open, but contains an open containing x. Are we okay with this one? Let's do 2 implies 1. So now here we have a basis. Assume Bx is a basis, neighborhood basis, such that this thing. So I will not write the property again. We want to show xn converges to x. So we take an open set containing x. Let U open with x in U. And now we use that Vx is a neighborhood basis. Since Vx is a neighborhood basis, we know there exists some B in the basis contained in U. And now we use the property for B, we get the property for U. Hence, maybe let's say for this B, for this B, there exists some positive integer such that xn lives in B whenever the index n is larger than capital N. So I'm just using property number 2. And now we just use B is a subset of U. Since B is a subset of U, we also have xn lives in U whenever n is larger than or equal to n. And one if and only if 3 is an exercise. Will be a homework assignment. Of course, you can also use 2 now. So yeah, let me write something here. So this will be a homework question, and I want you to note something. I want you to note something. Assume we have a basis. Is a basis for the topology. And take a point. Then this thing here that I'm defining, the basic sets containing X will be a neighborhood basis. And any neighborhood basis looks like that for some basis. Yep.
The homework assignment will be, when we prove that 1 is equivalent to 3 or that 2 is equivalent to 3. Or we have a
Well, now you know you can do either. Yeah. You get to choose. Any other questions? Okay, so why should we care about that lemma? So some applications. So these examples are mostly applications of the lemma. The first one, example 1 here, will be metric space. That's where we have a nice neighborhood basis. So let's take a metric space. Let's take a point X in the metric space and consider the metric topology here. And let's take a sequence. So a sequence xn converges to X well, I can use 1 if and only if 2 for my favorite neighborhood basis. So converges to X if and only if for every epsilon, positive epsilon, there exists capital N such that xn lives in the ball here for every n bigger than or equal to capital N. Just applying the theorem for my favorite basis for my favorite neighborhood basis. So maybe I can write that. Here we have Vx, balls, open balls, centered at X. And this means, so what we're saying here is, for every epsilon exists n such that, how do we say that? Distance from X to Xn is smaller than epsilon for every n bigger than or equal to. So we're really getting X minus Xn is smaller than epsilon, but with a new notion of distance. Is that okay? So some more terminology. I will continue these examples after this. Definition 4. So a sequence, I want to say two kind of innocent things, but I want to fix terminology again. A sequence Xn is constant if it's constant, right? If there is a constant value, if exists X such that, so notice this is independent of topologies, it's just a sequence thing, such that Xn is X for every n. So of course, this is not what I want to define. The same sequence or a different sequence is stationary if it's eventually constant. If there exists some X and exists some n such that maybe you can play with the first, say, 100 value, 120, 100 million, but after that, you're constant, such that Xn equals X for every index bigger than or equal to your given n. So this is actually what I'm defining, stationary. And something I want to note, stationary sequences are always convergent. Right? In any topological space, every stationary sequence converges to the stationary point. Right. Do you need me to write an argument why this is true? You take a neighborhood of U, then of course the sequence will eventually live in that neighborhood because it's just X. So yeah, if you're not convinced, please write down an argument. And now, second example here, example 2. So what we're trying to get into now, we're not going to finish this today, is probably you don't know this, but in the real numbers, you can pretty much describe the topology using sequences. That's mostly because you can describe closed sets using sequences. We'll see that at some point. That makes sense, right? If you're in an open set, like say an open interval, then you can get a sequence converging to one of the extreme points in that interval, but the extreme points do not live in the subset. Now, if you have a closed interval, then any sequence inside that closed interval that converges to something will converge to something in the closed interval. So you can describe closed sets using sequences. We'll get there some point next class. So we're trying to get there. Can we describe the topology using sequences? And the answer is, well, will depend. So example 2, let's take a discrete space. I want to give you some pathological examples, be a discrete space. But this, I mean, any set with a discrete topology. Can we have convergent sequences in X? Each point is open. So if you're a sequence that's going to converge to something, eventually you need to live in a singleton because the singleton is open. So you need to be stationary. Then the only convergent sequences in X are the stationary ones. And if you don't have that many convergent sequences, then maybe you cannot use sequences to say much about the topology. So do you see why this is true? So the idea here is if xn converges to X, use that the singleton X is open, then there exists some n such that the sequence lives in the singleton if you let your index grow big. But that means you're just X. So you need to be stationary. And of course, we know stationary sequences always converge. So I need to prove one direction. Let's use this space. I will switch colors because I have to. Example 3. Now what I want to do is so remember we introduced the co-finite topology and we introduced the co-countable topology. Didn't focus too much on that one. But let's take a set. So in the set X with the co-countable topology. So the co-countable topology is, let's use TC. C comes from countable. These are subsets of X with countable complement. So subsets of X with countable complement. X minus U is countable. But I also want to allow the empty set here. So just to don't care too much about how big X is, either X is countable or U is empty. So open set here, we don't really know how big X is, but suppose X is not a countable set. Suppose X is like the real numbers. So open sets if the complement is countable, that means the complement is kind of small, then the set needs to be very big. Right? So neighborhoods here Well, you have a lot of neighborhoods. Anything that's kind of big will be a neighborhood. And if you do that for any point, you will get like a lot of neighborhoods. So let's continue the example over here. Again, and this one is not obvious. The only sequences that converge on this space are the stationary ones. So we need to take a convergence sequence and deduce it's stationary. Well, let's prove this. If we have a sequence, if xn converges to x, so the point x, we need to prove xn is going to be eventually x. We consider this set. We want a set with countable complement. So it's going to be like x minus something countable. We do have something countable here. The values that you get with your sequence. That's open. Right? Complement. The complement of this set is the sequence, which is countable. The only problem with this is this might not be a neighborhood of x. But you can always add a point. Because the topology only cares about the size. This will be open. This U is open. Right? The complement is the complement of this set is values that you capture with the sequence. But you need to get rid of x. Right? Maybe x is not even there to begin with, probably. So it's countable. And it's a neighborhood of x. It contains x. So we know, since the sequence we're assuming converges to x, we know there is going to be some positive integer such that xn lives in U for every n bigger than or equal to n. And now we're in trouble, kind of. Because if you live in U, but U, by definition, does not contain xn's, you're saying xn lives in U, then xn needs to be x. Xn is x for every n bigger than or equal to n. Because you cannot live here, but you live in the union, so you need to live here. Is that okay? Yep.
Why don't we like, but the U here is like given in some format. Shouldn't we just have some?
Yeah, this is very tricky. This is like, I'm trying to prove something kind of strong. Namely, if you give me a convergence sequence, then it needs to be stationary. Now here we'll need to spend like 10 minutes trying to find an interesting open set containing x to do something about it. So this this is a clever idea. That if you don't have it, you'll need to spend like half an hour trying to come up with something like this. Yep. Oh, that's the definition of the co-countable. It's sets with countable complement. It's kind of the co-finite. When you say sets with finite complement, here's countable complement. Right, that means you have a lot of sets. That means you have a lot of sets. Take your entire set, then delete some, something like this. Delete some like countable set, then you get an open set. And the thing that you're deleting here can be arbitrary. Particularly, this xn will work. Yep. So that's one example. Another one. Now, let's take X set with the trivial topology. Now, the question is, what are convergence sequences in X? Remember, convergence sequences say something about open sets. You only have one open set. So then every sequence converges to all points. Right? Let's prove this. If you take a sequence, given any sequence, and any point, there is only one open set containing X. Because it lives eventually, actually always, in the unique neighborhood of X. The only open set containing X is the point X is the entire set X. And we know that Xn lives here for every n. Let's say for every n bigger than or equal to 1. So what's going on here is something like, once again, sequences can be very good, but topological spaces are very general. So we will not be able to describe any topology using sequences. That's kind of a shame, but we'll work towards that direction. Which topologies can we describe using sequences? That's kind of the question that I like to answer now. And this is not how textbooks usually look at these things, but that's how I look at these things. Which topologies can we describe using sequences? And by that I mean, you need to be able to describe a topology by describing all sequences that converge in that topology. So can we do such thing? What will be the restrictions? Well, this is very bad. Of course, here we cannot do anything. If every sequence converges to everything, then probably you need to be discrete, let's be honest. In that case, you could be able to describe the topology. But then some other scenarios, like the trivial one, only constant sequences converges, well, you can still say something. So maybe we can say stuff, right? Maybe we can say stuff. And that's where we're headed. Okay, last 5 minutes. Need more space. This is the first. So far what we've been doing is kind of studying general topological spaces. Then what we did is kind of study topological spaces coming from some families. For example, those coming from metrics. Those are very good. But the fact that you come from a metric is kind of weird. So what I mean by this is, if I'm giving you a topological space, how can you decide if it comes from a metric or not? That's a very hard question. That's a very hard question. Now, what I want to do is maybe get something easier than that. I want to impose some properties on a topological space. So this is our first property. Let me switch this. Okay, first property. Definition 5. Topological space, let's call it X, is said to be a Hausdorff space. Hausdorff, this is a D. If for every X and Y points in X, which are different, if you have different points, you can distinguish them using open sets. There exist open sets U and V with X in U, Y in V, which are disjoint. So the picture is something like, here's your X, here's your Y. If you know they are different, then you can separate them using two open sets. So these things will not happen when open sets are just too big. For example, if your set is trivial like this one, then that's not true. Take any 2 points, there is no two open sets distinguishing. But if you go to something like maybe let's not say much about examples. We'll do that next time. I want to leave you with a proposition that we'll prove next time. Proposition 6. So the slogan here is, in a Hausdorff space, limits are unique. So assume X is a Hausdorff space. If a sequence Xn converges to points X and Y, then X needs to be Y. So this is what we'll prove next time. And as examples, example 1, discrete spaces are Hausdorff. Right? Just take, if you have X different from Y, you can just do X and Y, which are disjoint. And of course, metric spaces. If you take 2 different points, then what you can do is consider these 2 balls. So what I'm doing here is, I have a distance. If you take the distance by half, you'll have these joint balls. And this R should be distance between X and Y. which is positive because they're different, divided by 2. So this is what we'll study next time. And now let me stop the recording.